Hi, everyone. My name is Paul Bemis. I'm going to be presenting to you today some information on hyperscale data centers. I have with me Kevin, who's a co-presenter. He's going to be here as well. Kevin is a new support engineer that's working for our company, and he's going to be helping me to answer questions. He's going to be helping me to essentially ask your questions. So during the webinar, if you do have questions, instead of turning on your mics, which does become somewhat problematic from an audio point of view, just use the question or chat session here in the Q&A in our Teams meeting here. This is Teams webinar. It's a little bit new to me, so if I make mistakes, please bear with me. But he will prompt the questions as we go. I try to make these as interactive as possible. It's more interesting for you if they're interactive. So don't be afraid to ask a question along the way. Just type it in. I'll try to pause periodically and see if there are any questions. So today we're going to be talking about hyperscale data centers. And I've been around computing for many years now, 20, 30 years. I was a design engineer on computers back when I was a kid, a young engineer. So I've seen a lot of this. And the word hyperscale is an interesting word. Hyperscale really just means large. It just means, and it also implies some level of symmetry in the design. So we used to call it supercomputing back when I was younger, and these were big central processing systems. The one that everybody sort of remembers is the Cray supercomputer, which in its early days was liquid cooled. Seymour Cray was the founder of that company, came from CDC. There's a lot of history here, and the names have evolved, and I don't know where hyperscale came from. The term scale has to do with the fact that they're just getting large. These places are getting very, very large, hundreds of thousands of square foot of data center space, and there's a lot of symmetry. And I'll show you how that all works, and I'll show you how we model it in CoolSim and what to look out for as we proceed. Just so you know, most of you know me. I'm Paul Bemis. We've been here 18 years now, believe it or not, doing this. I came from the Ansys Corporation, which was also the Fluent Corporation. Those two merged. I was responsible for various products at those companies, all the products at those companies. My background is mechanical engineering and originally fluid dynamics, as a matter of fact, incompressible flows, not compressible flows. Nonetheless, I was the product manager for the head of product marketing for all of the products at Ansys and Fluent. Here at this company, I started in 2008. I saw an opportunity to go satisfy a market segment with a unique product that we weren't offering from those two companies. And it is represented in CoolSim. CoolSim is a SaaS-based model in the sense that the computation is done on a cluster by us. We take care of all of the complexity of mesh solve post for you and deliver results. You build the models, submit the models. Our responsibility is to make them run and give you meaningful results back. So that's who we are. Few definitions before we get started. HAC and CAC. HAC is hot aisle containment. CAC is cold aisle containment. I prefer hot. Doesn't really matter as long as you contain. The idea here is to separate hot from cold. You know, heat exchangers, as you're well aware, work best when the delta T is high. They perform better. They're happier. It takes less work to get them to dump heat. So separating hot and cold is something that evolved in around the 80s, 90s, that we began to separate hot and cold and then put containment around one or the other so that they didn't interfere with each other. Most IT equipment today is front to back cooling. So it ingests air in the front of the servers and dumps it on the back and into an aisle. So we separate hot and cold, and that increases the efficiency. It also lowers the energy. Remember, energy required for cooling is work. It's because you have to, at the end of the day, turn a shaft to compress, to drive the heat up, to use the Rankine cycle to dump it to the atmosphere. In order to do that, you need a good delta T. That means the return air and the return water or whatever gas needs to be hot. The hotter, the better. New modern equipment is built such that if it's hot enough, they don't compress at all, or they will trim. In other words, they compress a little So energy efficiency in the data center is all about getting the hot and the cold separated from one another. That's where it starts. And as a result, it has an effect on things like N+1, because when you contain like that, it's really great thermodynamically. But if you have a failure, you now have a pressure variation, because you're trying to blow air into a high pressure environment if the cooling units are down and it's contained, for example, on hot, or vice versa on cold. So it's important to make sure that you understand what happens in a failure mode situation. And that's the purpose of modeling, is to understand what we call corner cases. Modeling is generally, CFD modeling is generally not about steady state operation. We assume that all of you are smart enough to do the math to figure out you've got enough cooling in the room for your heat load. But what happens during failure analysis, or what happens during high temperature operation? That's really what you use modeling for. We used to test for this in the old days. You know, we called it four-corner testing, test the four corners of the design. Here, that's the same idea. We're testing the extreme conditions to understand if we add that much IT load, will the system hold up? If I lose a cooling unit, what will happen? That sort of thing. What if? That's what it's primarily used for. A few definitions before we get started that I like to use. These come from the DOE training, Department of Energy, what we call DCEP training, Data Center Energy Practitioner training, that is put on by the Department of Energy every year. And I tend to do this section. I do the airflow section for them when they deliver that course, when Jorge delivers that course. A few definitions here. RTI, return temperature index. You can do this as delta T's, is often how they promote it, but I'd like to do it as airflows. They're synonymous. So here we're looking at the rack airflow, the flow that the rack needs. Remember that we're talking air cooling here. We're not doing liquid today. We're doing air. So in order to dump the air, you need a certain amount of flow rate, according to, of course, the convective heat transfer equation. It's mass flow rate times density times delta T is the heat that you're dumping. And at atmospheric level, that turns into, for today's servers, about 125 CFM per kW. And I'm afraid for my international customers, I'm going to use American units today. So I'm going to use CFM. So about a 125 CFM per kW is going to be in the numerator. Denominator is how much air are you throwing at the problem to take care of the numerator. You want that denominator to always be bigger than that numerator, or else you're going to have, particularly in a contained case, pressure differential, the incorrect pressure differential. If this number is bigger and you're contained, then you'll have a positive pressure differential between the amount of air being supplied and the amount of air being consumed by the racks. That's the goal, is to have a positive pressure differential across the rack. So the air goes in on the front and goes into the return system. Times 100 equals RTI. So you can see you want your RTI less than 100, right? Because if this number is bigger than that one, you're going to have a decimal times 100. You want it less than 100. If it's greater than 100, you've got pressure problems. There's another one as well called the rack cooling index. This is a little more subtle. This is how many hotspots do I have, and is it a problem? You can think of it that way. This is 1 minus the over temp regions on the rack inlets. We're talking about rack inlets here only, divided by the allowable over temp times 100. Now, these were originally developed. There is also an RCI low, by the way. This one's kind of irrelevant from my point of view, because running the racks too cold is not a problem, really, other than energy. It's an energy hole, you might say, in the ground to which you're pouring money, but it's not going to hurt the servers. So it's really high. You don't want hotspots for a couple reasons. One is it damages the servers, of course. That's what we're concerned about. Number two, they have their own control system for airflow, and they'll ramp up. So what'll happen is if you get those server inlets above 80 degrees, the number we always use is about 78 Fahrenheit. You get it above 80 degrees, which is the spec, 80.6 is Fahrenheit is the upper spec for ASHRAE recommended. What happens is the servers start to ramp up. They go to full tilt on their airflow because they're variable speed. And now you have asymmetries because you've got servers running at much higher CFM than 125. I gave you a number of 125, but when those things ramp up, they'll double that. And now I've got servers on one side of my room that are pulling a lot more air than on the other side because I have a hotspot, I've got asymmetry. That's a problem. So you generally want them to run in the ASHRAE allowable range. Not everybody does that. I do have customers running in the allowable instead of recommended, which goes up to 90 on the inlets. But most people try to run in the recommended range. Okay. Now, I also want to just remind you about our friend Mr. Bernoulli. For those of you who may not remember your fluid dynamics courses from sophomore year or junior year, we have a couple different parts to pressure. One is the dynamic part and the other one is the static part, and they trade places. We're not going to pay much attention to this one. This one's height. So yes, pressure changes with height, but most data centers don't levitate, fortunately. And they don't work at high altitude, although, there is a density number that we use that's at atmosphere that can be adjusted for altitude. So altitude does play, but it's not a dominant characteristic. The two that we work with mostly are dynamic pressure and static, and they trade off for one another because, of course, rho AV is constant, right, from our friend Mr. Bernoulli. So dynamic pressure trades off with static pressure. So way to think about it is total pressure is the sum of static plus dynamic for most things we deal with. You'll notice this in, for example, underfloor designs, raised floor designs, where you're near the cooling unit, the static pressure is low, the dynamic pressure is high, and sometimes you can take a piece of paper and just drop it on the floor tile and it will pull it to the floor because the underfloor velocity is so high that there is no static pressure, and in fact, there's negative pressure. So negative static if the velocity is too high. So it's important to keep these things in mind. I'm going to remind you as we go along about this. So just wanted to remind you of that. Now,
Paul, a quick question,
sure,
actually.
absolutely.
So can you go back a couple of slides when you were talking about the RTI? So earlier you said that you want the value to be, I believe, less than 100, but are there any cases in which, say, the RTI can be too low? Like, can that be undesirable?
No, it's just a waste of energy. And it
Gotcha.
generally doesn't happen, Kevin, because we're all using VFDs, and the VFDs will generally modulate to whatever you need using a pressure sensor. So having too much air is like having too much cold in a data center. In other words, it's not going to hurt anything. It might feel like a hurricane in there, but it's not going to really hurt anything. It's just that it's a waste of energy because remember, fan energy is cubic in nature. So the power for a fan increases as a cube of the rotational velocity, or the CFM. And for the compressor, having too much air means the return air temps are going to be unusually low. And that means I have to lift, I have to pressurize, I have to do a delta P on that to get it up to temperature to dump it to the atmosphere. So my lift is higher, my work is higher. So having too much air is not critical from an IT point of view for cooling. It's just an energy problem. It
Gotcha.
consumes much more energy.
Okay. Thanks.
Okay. Sure. So I'm going to show you 3 levels of increasing detail. We get into this a lot in CFD. The question becomes, how much detail is necessary? And, I think it was someone smart like Einstein that said, only as much as necessary. I'm paraphrasing. But you can put too much detail into a model and it'll run a long time and you'll get the same answers you would if you simplified it. So we over the years have gotten comfortable with a certain level of detail for getting answers out of this system with CFD. And there's 3 levels you can work with depending on your needs. Level 1 is assume the racks don't leak at all, but the containment does. The second level is assume the racks don't leak, but the containment leaks where it intersects the containment. And the third one is assume everything leaks. So It depends what you want to do, how you want to do it. I'm going to show you these in somewhat detail. Let's first take a look at the anatomy of a rack. So this is an IT rack, a very typical IT rack. It has a front door. I've built this in CoolSim. It has a front door here. It has a back door, typically. The servers sit inside. They sit in rack rails. This all dates back to the early days. In fact, the width of these servers is typically 19 inches for historic reasons. Manufactured by Americans, the 19 inches, believe it or not. And they still run at 19 inches for the most part. Some of them are wider. There's also here a rail, rack rail. So if you open the door of a rack, those of you who are near one, you'll find that the servers are sitting in there in slots. They're called U's, believe it or not. A U is 1.75 inches, believe it or not, or 3.75 inches, believe it or not. It's always been the same. And those are the slots. And they leak. So the rails typically leak, and there's a gap at the bottom where it leaks as well. The doors are not really consequential. The doors, you really don't need to model because they're pretty much 80–90% area open. And if they're not, that's a problem, right? You don't want the door restricting airflow because the air is going front to back. So this rear surface and this front surface really don't even need to be there. They could be eliminated. They're not, of course, because people have doors on their racks and you like to close them. But they need to be highly open, and therefore we don't worry much about them from a modeling point of view. It's rare that I ever model doors. Another way to say it is, if you've got a door in the model and you're modeling it and the door's a problem, then that's not a CFD problem. That's an equipment problem. Get the door off it if it's restricting. But the rack rail is important, and that's the one you want to model because it leaks. It leaks on the sides, it leaks on the top, leaks on the bottom. Okay. Typically you have 6 inches at the top, sometimes a little less. You have 3 inches on either side. Typically, I'm using inches again, I'm sorry. 6 inches at the bottom. So it's really the servers. When we talk about rack inlet temperature, it's not the rack itself we're measuring, it's the server inlet temp, the average server inlet temp. And you see here, I've defined this one. You can do this in CoolSim. You can define your equipment. So I've got an IBM stuck in there. That looks like a 5U. Got an HP stuck in here. That's a 5U. And then storage down here. That looks like 15, probably U. They all come in U's. One slot. I believe the number is 3.75 inches. I haven't looked at it in a while, but I think that's it. So what you want to model is the rail. You want to model the leakage around this. I'm assuming that the customer, your customer, or if you're doing this yourself, your servers have blanking panels in it. That's what this is. The black is a blanking panel. So if there's no equipment in the slot, there needs to be a blanking panel there. If not, start there. It doesn't have to be complicated. You can use cardboard. I've seen that done. In fact, they have some cardboard that's not flammable that you can use magnets and just stick them in. I mean, blanking panels can be expensive because there's a lot of them. And people sometimes will say, well, I don't have enough money for the blanking panels. Well, that's okay. But do something, cardboard. Well, cardboard's flammable. Well, there's cardboard that's not flammable, and it's been used very effectively. I can't remember who produces it. I could look it up if you need it, but there is a flame resistant perforated cardboard. I've used it. And you can buy magnetic strips at the hardware store. I've seen a lot of this done, and it works well. You can use plexiglass, whatever. Get something and blank your racks. So rack leakage can be an issue for hot and cold L containment. It usually is the issue. And you can create a rack assembly that is best practice for hot and cold L systems. You can build each one of these out of CoolSim using an assembly. But let's go through more of a practical approach of how you do it in CoolSim. So here's a design. This is one we're going to be focused on today. This is kind of a hyperscale design. The hyper means it goes into that direction, the in direction, somewhat into perpetuity. It just keeps going. And it sometimes goes in the other direction as well, where you'll have multiple sets just like this. And they're separated by an aisle usually here, and then you'll have another replica of this. So just hyperscale just means it goes on, and they're all the same for the most part. Now, level one is I'm going to let this surface here leak. This is the containment surface where hot oil contained here. Here are the servers. You can see these little arrows indicate airflow. So it's blowing into the contained area. There are grills at the top of this that are probably hidden. I don't see them. But you can let this surface leak. Generally, we let it leak at about 5% using a baffle object. That's a perforated plate. You can think of it as that. And doing it this way is quick. You can lay them out really, really fast, but it doesn't, this one's pretty coarse in its representation. It does not focus the leakage anywhere. It's letting it leak right through this whole surface. And the way leakage is often set, you'll have people say to you, oh yeah, assume 10% leakage. And the question I always ask is 10% of what? 10% of the total amount of air? 10% of the surface area? What's the percentage of? And I've never gotten a clean definition of the percentage. In this case, what we're doing is we're letting the material leak. It's called porous media in fluids terms or fluids talk. Here I'm letting it leak at 5%, which is the default number on the baffle for our software CoolSim. So we let it leak at 5%, air goes in. And it's a large surface. So a percentage of a large surface is a fairly large number. So level one's okay. It's quick. It's easy. I tend not to use it anymore. We used it originally for quite a period of time. It worked well. But as you crank these things up, I tend to go for a different level. Level two. So now level two here is focusing on the area of the intersection of the rack with the contained area. So I'm looking at right here. So here, I let this one now be set to no flow. By the way, don't use zeros in CFD. That's a mistake. Solvers don't like zeros. So we put switches in. So there's a switch right here that you can uncheck. It's normally checked. Uncheck it. That will make it a solid surface. It will not allow air to leak through it. So now I've sealed up this upper section. And that's not leaking because they generally don't. They're made of solid material. The end caps are generally made of solid material. The leakage occurs here. It occurs around the perimeter of this rack. So you can set the rack up off the floor by a few inches. You see I've got it up off the floor 3 or 4 or 5 inches so that underneath that rack I can model the behavior of leakage. And I've put a baffle. Now in CoolSim, a baffle, we have a system priority. Hierarchy. So the second one has been added to the system. It's most recent. Whatever object is put in the model or most recently has priority. So these are coplanar, but this one has priority, this leakage, because it was put in there second, put in there sort of last. I do the leakage rails last. And you see I've got it turned on, and I've got it set for 10. So now I've by the way, named it. That's important to name it rack leakage, because when you want to vary that parameter, it's important to have it name something other than a default name of baffle or baffle underscore something. So I named it, which is a good practice, and I set it at 10%, and I made it just a little bit taller and wider than the rack. And I let that leak because generally leakage occurs where the rack intersects the containment because someone didn't do it correctly. They didn't tape it. This is much like, construction and homes. I do a lot of other consulting, and right now you're trying to get your home tightened up for energy efficiency by eliminating all the leaks. We don't want it leaking here around here. But from a modeling point of view, it's important to assume it'll leak a little, because the world is not perfect, right? And that represents good best practices. Now here I've gone one step further. Now I put a gap between the racks, and I made these racks a little bit smaller than normal. In other words, if the rack is 2 feet wide, I'm making it 19 inches because I want 3 inches on either side of that rack to be leaking. So here in this design, what I've done is gone to one more level of complexity, one more level of detail, where I'm actually modeling the rack rail in addition to the leakage around the rack using one surface called leakage, right? Because we don't know in the real world where the leakage is. It could be around the servers. It could be the rack rail, could be top, could be bottom, could be where it intersects the cabinet intersects the containment. All of those surfaces could leak. You could define them individually and try to put those in, but that's complex. What we do instead, to save time and be more efficient, is represent it with one surface. So here what we've done is simply take the racks, put a gap between them of 6 inches, 3 for either side, get them up off the floor a little bit, make them not quite as wide. Remember, it's the server that we're trying to model here, not the rack. We really don't care about the rack itself. We care about the inlet of the server. So we give it 3 inches on either side, 3 underneath, 3 on top is good, and then put that leakage parameter in there at 10%. This is really fast to do. It's easy to do. We've just recently modified the software to make this even easier to do, and you can bang these things out quick. Okay. So let's talk a little bit about Hyperscale and how, I just wanted to show you how we would model that and how quick it is to do that. So I'm going to take the risk here of opening up CoolSim and dragging it over and showing you how we do this. So here's this data center here, and I'm just going to go to full screen. I've done just one of these. This is just representative of the situation in general. I mean, this is a small set, but it is a fan wall based unit. And that's generally what you find. You find fans on either side. So these are big structures. These are usually 10 by 12 fan walls. There's multiple fans in them. They're chilled water. Most of you recognize this structure. This is a structure that's been very popular now. If you're building data centers for Yahoo or Microsoft or whoever, this is the kind of structure that they're basically building or want you to build. Fan walls on either side, blowing to the center, non-raised floor design. And the issue here is getting enough air. Remember that we're looking at 125 CFM per kW. If you're going to put 40 kW in a rack of air-cooled IT, you need a lot of air. And so getting enough air in there has basically precluded raised floor. You really can't do it with raised floor anymore. The raised floor gets so deep because, again, velocity. We'll go back to the velocity, the Bernoulli issue. What happens is in a raised floor design, that underfloor velocity gets so high you can't get it out of the floor. It goes by where you want it to go. You want it to come up out on the edges, particularly the edges of the racks. It won't come up. This is generally how they're doing it these days. These big fan walls. This structure right here is generally a diffuser. That's got some percentage open in it. So this is a screen that they use to try to unify the pressure in the case of N+1. One of these fan walls goes down. They want that air to be distributed. It doesn't have a lot of resistance. We generally set them for about 70% open, but it does supply some diffusion of the air on the back side of this from a pressure point of view, so that if I lose one of these units, then I get the help from the other one because it's coming in this direction a bit more due to that resistance. So a little bit of flow impedance can help diffuse the air. Return grill, so the air is coming up and around and looping. Okay, so that's generally how they're laid out. They get bigger. They go in both directions. They go in this direction, back and forth. You can have multiple of these pods. I generally call them pods. And they obviously go in this direction. Now, to lay them out, we have implemented a couple of nice tools here that work pretty well. So I'm just going to open the rack editor here and show you how we did this most recently. It seems to work quite nicely. So what we have now in the editor for CoolSim is a gap. You can just put a gap in here. So I've got space between racks at 6, and I've got 13 racks. So that's really kind of nice. All I have to do is pick the rack size and then put the quantity in and then put the gap between racks in. You see, I have it up off the floor by, in this case, 3 inches. I have the length of the rack can stay whatever it is. It doesn't matter so much there. You see, I've got the rack at 19 inches wide, and I've got the height at 80.5, which we have a U figure here is 46 U's. I want to represent all the U's. Remember, I'm really modeling servers here. So this is a 46U rack. I got 46 slots in it. Each slot is, I think, 3.75. I can't remember. Well, I should be able to, well, it doesn't matter. Who cares? But you've got 46 slots. Okay. So that's that, and by the way, I've got this thing set right now at, in this case, 100 kW per rack, which is where we're headed, but we're dumping 60% of that to water. All right. So these are operating at a net 40 kW of air. So I've got that set up, and I feel pretty good about that. I want to position this. Now I just want to replicate it. Now you see I'm a little bit off here. The gap up here is not the same as the gap down here. So I'm going to move this down just a little bit so those gaps are uniform. Now we have this really nice feature in CoolSim called clone. So I'm simply going to clone it. I'm going to clone it 3 feet. In our case, it's X direction. So I'm gonna it's actually, I think, not 3. I think it's 5. Hang on a second. 3 is too tight. So you want the hot aisle, that's what I'm building here, the hot aisle to be wide enough to meet your needs, okay? I've got a 6-foot hot aisle. So that's really what I want, is something wide enough to be able to handle. And I'll show you, if this number gets too low, you run into pressure problems where the center, the hot aisle, becomes pressurized. Again, due to the fact that we're moving from high velocity air to no velocity air. So if this is not wide enough, you'll get a pressure gradient in the center of the hot aisle caused by 2 flow streams intersecting with one another. So I'm 6 foot here, that's fine. I'm going to take my rack and I'm just going to clone it 6 feet. And clone is a copy paste with offset. It's a really handy little tool. A lot of people like this about CoolSim. We've got 6-foot offset in the X direction, and I just apply that, and didn't go far enough. So let's put it over here. I want to line these two up. So I didn't obviously get my offset. I forgot the width of the rack. Align to zoom in. You want to align these. So now I've got my rack over here. I want to change that airflow direction because, of course, the airflow is in the wrong direction. It's blowing incorrectly. We have a switch for that. You don't have to rotate it or change it. All you have to do is change the airflow direction, reverse flow. All right, so there's my reverse flow direction. Now I've got it flowing in the right direction. I want to put a containment over there, so I'm going to select this guy, and I'm going to clone him 5 feet. So distance along X, 5. So there's my second surface over there. I don't know what I'm doing wrong here. Oh, it was 6 feet, sorry. But you can always fix it. Just align. We have these aligned. So align to X max, and it just lines it up. You want your corners to look like this. The reason I'm bringing this up is that alignment is very important in CFD. Alignment is what separates you from failure, in a sense, because you want these things to be aligned properly. This one's still a little tight. I'm going to move this over. You want this gap in this aisle to be where you want it. You want it correct. So I'm going to go in here and fix this a bit. I'm going to move this over, this rack over a little bit. It's starting at 13.86. I'm going to start it at least at 14. Let it move over a bit. So that's a little bit better. Might go a little bit more, 14.5. Just move it over so that you have enough room in that hot aisle. You want to, here I'm about 5 feet in that hot aisle. That's really what I want. It's closer to, you want these to be as wide as you can possibly get them. It's expensive to do that because, of course, you're spending money on infrastructure. White space is important. But nonetheless, you want these things to be wide so that you do not have pressure problems. So now I want to clone that end cap, and I don't know the length of this one. So the dimension is, it's in meters right there. So let's 28 feet. So I'm just going to take this structure right here at the top. This is the end cap, and I'm going to clone it at 28 feet in Z. So in the Z direction, I'm going to go 28 and add it in there. So I apply that, and there's my end cap. And the great thing about clone is that because it's a replica, it lines everything up perfectly. So you see, that's what you want your end caps to look like. And you notice I've got these set at 0. So there's no leakage on these at all. The leakage is switched off. So if I go to the airflow panel on that particular UI, you will see under airflow, I've got it switched off. So there's no air leaking there at all. And but I've got this new structure here that I've added. I've added this later. I usually color these because when they're coplanar, they're hard to see unless you color them. So I've made this one red. This is my leakage rail, and it's a little bigger than the racks, and it's a little wider. So this is going to be how I define leakage. And you notice here I've named it rack rail leakage, and I have it set at 10%. So this is just a nice little structure to put in after because it represents the leakage, and I'm going to show you later why that's so important. So now here's my rack rail leakage. I'm going to want that right in between here. I'm going to leak right on this rail. By the way, it helps if you, this is just, I'm going to clone it right now so that I can have a second copy of it. I want it over at 5 feet, actually 6 feet. So the distance between this section is 6. So we made a second one there. So I have it to be able to use. And I want to line these up and I want these to be coplanar. So I select them, I close gaps in X. That one's in. I take this one and this one. Hold the cursor over the one you want to hold still. Close gaps in X. X is the horizontal direction. Boom. So there's my containment. And you know, the containment defaults in CoolSim to go right from the floor to the ceiling. So when you drag a baffle in, it goes right to the floor to the ceiling. And you see now, I've got my leakage in there. It's defined. I'm up off the floor a little bit, so it's going to leak underneath. It's going to leak in between. If I have pressure problems in this room, it will show up. All right, and now I'm going to simply put in my ceiling grills. I have them over to the side so you can see them. I want those lined up too, so I'm going to line those up on this surface. So I'm going to close gaps in Z. This little close gaps tool is just very handy. And I'm going to close gaps in X. Okay. I probably want to clone these two guys. So here I can make a group. I'm going to group it. I'm going to offset them. So now I'm going to clone this. I don't know exactly what that distance is. I don't really care. I know it's lined up on this edge. But I can move it, or I knew it's going to be more than 6, so I can make this like 7 feet. Doesn't really matter because I'm going to align it anyway. So now I've got it over there, and I just need to align it on the edge of this, align to X max. Boom. Okay, now I have a pod. Pretty nice. Now I can group this guy. The great thing about CoolSim is you can clone the entire structure. I'm going to group it, and now I'm going to clone it. And I can clone it n times in this direction. This is why it's so fast to lay these out as I can group it. If I know what my offset is, I need to know this offset. I need to know the distance between this edge, the very next edge. But I know that because I'm a design person. I've laid that out. I think I want 3 of these. It'll give me an error if it's too many. I want 4 of these. I'll do 4 at 28 feet. It's going to take that entire group structure. It's going to replicate it and clone it. Now, it says it's going out of the room. That's because I have too many and I didn't do my math. So I'm going to reduce this quantity to 3, and now it should be fine. Now I hit the apply. Now it says they're still going out of the room. X, 3. Let's do 2. Maybe my distances aren't good enough. I think I wrote down what this offset is. 22 feet. I've got it wrong. So the offset should be 22 feet. Let's try it again. In any case, you can make mistakes here and it doesn't really matter. You can just erase them. So let's try one of them. We'll just do one of them at 22, make sure that offset looks good. So 1 at 22, let's have a look. So I apply this and it creates an offset. So there we go. Now that offset's not too bad. That's a pretty wide aisle there. It's up to you. That aisle is certainly wide enough, probably a little wider than you need it to be. So maybe that offset should have been 20. I can edit the entire group and move it back. So I can take 2 feet off the X direction. That would be fine. So I go for 25 on start X. And the reason I'm showing you this is just to show you, basically how easy it is to do this. So now I know my offset should be more like 20. I'm going to lay in a couple more at 20. So I'll put in, looks like I might be able to get 3 at 20. It'll tell me if it's too many. It'll do the math for me. So 3 at 20. Yeah, says now you're not going to get away with that, Paul. How about 2 at 20 and lay them in? The point I'm simply trying to make is that once you lay out one of these pods, replicating them is basically a click. You group it, which is a rubber band. You do a group. The group gives you the object tree. If you ever wanted to open it, you can edit the group. You can rotate the group. You can and this group editor is getting, you can change parameters of a group. You can change the path details, grilled teeth. So, there's quite a bit that we've added into this tree structure. The tree structure on CoolSim is not over on the left. Many Ansys and other codes put the tree structure over on the left. We wanted to give you the room to be able to see properly, to be able to get at the geometry and view it. So we gave you viewing area. If you ever do want to see the tree, Control T, the tree will pop up and you view the tree and you can edit any one of these if you want. Okay. This is not intended to be a training session. So, but I simply wanted to show you how quickly you can build these things and replicate these structures. Because once you've done one and you've got the detail in one, again, we go back to the name Hyperscale. They're all the same. They're scaling up a structure. These are HDUs at the ends or PDUs. These are the KVA devices that are feeding the power to these guys. And yeah, I mean, they're all the same. The beauty of that is that you can group it and replicate it using clone command. Okay. So I just wanted to simply show you how to do that and why it's so quick to do it in CoolSim. All right, results. Now I've run a series of this. In CoolSim, you can run up to 4 variations off of one setup. So this structure right here, I've set up and run already, so you didn't have to wait for it. And I've done 4 variations on this one. You can run up to 4 concurrently off of one model. There was no particular reason why we chose 4. Except that we do download results and we thought the downloads would be too big. But in the future, you can expect this to continue, run 3, 4, 5. You can run them all at once off one model because the model is fundamentally not changing. All you're changing is parameters of the model. So you can see in the first run, everything's on steady state. It's fine, right? That one's probably going to always be fine. We're not worried about steady state generally. What we're worried about is when you turn a unit off, when you lose a fan wall. And position makes a difference. Now I didn't do the full, this scrolls down, but I did hyperlink this. This is another nice feature of the way we do things at Applied Math is we hyperlink. So this is a PowerPoint or a PDF, doesn't matter. You notice my little cursor looks like a hand because it's a hyperlink. I have linked this image to a set of results. A set of results popped up on my other display, and here are the results. And I can take this, by the way, this link and share it with those of you in the audience. If I can only find you. I know you're here somewhere. So in your chat box, if you go to chat, Control V, you will see a hyperlink for this output. So in the new version of CoolSim, we allow the sharing of output via hyperlink. At the end of the run, at the end of a simulation, you will get a email with a hyperlink. And the hyperlink allows you to view the results dynamically. And by the way, you can do this from your phone, which I tend to do, much to the chagrin of those around me. I'm looking at results. So here I've shown you 4 sets of results. And the reason I hyperlinked it is so I could scroll it. You can't do that in a presentation form, but you see I've shut different runs on and off. It gives you a summary at first, and then underneath each one of these runs, which are simulations, someone asked me yesterday what a run was. Well, it's a simulation. So run 0 is I ran it first time, run 1 is I ran it second time. And we display 2 sets of information, numerical and graphical. Graphical is over here on the left. You push this little 3D files, you'll find all graphical over here. Let's stick with an overview of the numerical first. And I'm trying to be sensitive to time here, so it's 9:44. But we give you all the data you need to know. This one ran on a medium mesh. It generated 1.3 million cells. These numbers are important. Flow through the units, 560. Needed by the racks, 586. All right, so I'm already a little bit in trouble here, right? I'm only given it 560. Flow through the racks is 586. That's a problem. So let's go one step further and take a look at our energy report. We're above 100%. Our RTI is 105. So even in the steady state case, I have set this one up and I just ran this. I don't really even know when I ran this, but I can tell right away we're having trouble. And look, my RCI is showing 90. I'm getting into the red. I've got problems here because my airflow is insufficient. This could be for a variety of reasons. It could be altitude that's causing this. Could be this is up in the air. And even though I set my initial boundary conditions correctly to have enough air, I don't have the density. And so I'm having trouble cooling it at high altitude. It could also be that we have high temperatures running in this data center. Temperature will affect flow rate, again, because of density. So if we're running at a supply air temp here that's fairly high, let's take a look at our supply air temp down here under cracks. We're supplying at 77. Our return air temp's 103. At 103 Fahrenheit, you start to run into issues with density. It will change. Remember, it changes with temperature. So it could be that I've got some trouble. I can tell just by looking at the numerics here that all is not great. And if we look at our racks, so let's close this one. Let's look at our rack report. You see I'm failing. I've got failures here. Some are passing. So this is the recommended range here. You see this design does pass the allowable, which is higher. It goes up to 90 on the inlet temp. But we're having some trouble down here. So let's go look at it graphically. The most important one is ASHRAE recommended range. This is really the go, no go kind of gauge, if you remember that. And you see that my racks are having some issues. Not all of them, but some of them. And guess where? On edges. Guess why? Velocity's high. So right here, we've got very high velocity air coming from out of this air handler by this rack, and it's causing that rack rail to leak. And I've got some trouble up top here too. That's usually related to pressure variations. So this is not a good situation. My advice here would be, Mr. Customer, you've either got to do one of two things. You're not going to be able to run these things at the rated capacity that you've got them at. Right now, we've got them sitting there at 40 kW each. 40 kW of air cooling, that's about the upper limit for these kinds of designs. It gets difficult to get enough air in the room. If you take a look at what we're pumping in there, we're pumping in 560,000 CFM of air into a room that is only 7,000 square feet. That's a lot of air. So let's go take a look at the airflow itself. We'll take a look at, path lines. We produce these, of course. And by the way, these can be shared individually as well. So I can take this image because it's a hyperlink and I can copy it and just dump it into the chat box, and you can open that one. And this is all Ansys technology. This is, not ours, so to speak. We're a partner of Ansys. So you can do things here. This is their viewer, so you can right mouse click and hide. If you do a hide, it cleans the body up. I've just hid the outer surface. So now let's take a look, and a Y key will give you a top view, and an N key will take it off perspective. And you can see what's going on there. This is velocity. I have a lot of velocity happening right in this area. Look, we're pushing up into 900 feet per minute, going to these servers. It has to come around this corner. Geometry makes a difference. Here the air has to come around this corner and come in. The velocity is going to be high here. And it shows up in leakage. So I'll show you the leakage. We have thermal cut planes on this. So we go to some of the thermals. Let's take a look at a contour plane. And these are generated for you mostly automatic. I added a couple here. You can, of course, add more, but I added them. Let's take a look at temperature at Y equals 6 feet. So we're up pretty high now in the rack. I've done a slice. Let's do a Y key. Again, I can share this one with you if you're interested to follow along. So here is my Control V. So there's the link I just gave you, and you can open that. And if you hit the Y key on your keyboard, So Y, and you hit the N, that turns off perspective, and you get this view. This is kind of an interesting view. We can see leakage. Look at it. So there's my leakage rail right there. That black line that I'm pointing to is my leakage rail. You can see it's coming out. It's bleeding into the cold aisle. Why? Because velocities here are high. So as the velocity comes around this corner, or the air comes around this corner and past this rack row right here, I've got a low pressure right there compared to here. And what it does is it pulls the air through the gap and causes leakage to occur. Now, I could tell by looking at the RTI number that this was going to have a problem. That's why these parameters are important, is because you can tell by looking at a single number. That's why they did it. They wanted to show that leakage parameter in an RTI pretty easy. And you can see this one's leaking pretty badly. And then let's take a look at pressure. This is another interesting one that I was looking at. Take a pressure at the same point. Now, you want the pressure always to be positive in the room compared to what's in the cold aisle. Now, this one doesn't show it perfectly because I don't have the scale set right, but you can see the pressure here is actually lower than the pressure in the hot aisle. The hot aisle is pressurized in certain areas, and that's because you have two high velocity air streams coming at one another. You can see it here in rack path lines. Again, I'll share these. The entire report I already shared with you, but I'm showing you specific examples. So here is path lines of hot air return. And you'll notice that if I take a look, I'm going to manipulate the scene a bit. But if I go X and I rotate it around, yeah, I really want Z. So here's my Z shot. So I'm going to zoom in on this. I'm going to turn off perspective with N. So I use the Z key and the N key. And now I'm going to just hide this body because this is the cooling unit. I don't really want to see the cooling unit. I want to see what's behind it. And I can just keep progressively right mousing and hiding till I get into that. Whoops, I turned off the flow stream. So that's not good. So let me refresh that again. So here, I'm getting into a little bit of the Ansys capability here, but let me turn on those return path lines again. And what I wanted to show you is these airstreams banging into each other. So let me hide that. So there they are. So look at that. So what I've got here is air coming out of each of these servers, and as it hits the center, it turns. They bang into one another. Pressure rises right there. Static pressure is higher in the center of that stream because the velocity went to zero or near zero. As the velocity declines, the pressure increases, and that causes it to go leaking back around those rack rails. And you can see some of them coming around the rack rail right there, coming into the cold aisle. It's coming underneath, which is not unusual. You do see leakage under the racks quite a bit. People forget to look down. Get down on your hands and knees and stare under that rack and make sure it's sealed up tightly. Okay, so this particular one is going to have issues. We know it. We're in steady state right now, and we've got issues. Say nothing about, run 3. Run 3, I've got some of them turned off. So let's take a look here. I'm at 120. This one's in bad shape. You know right away at 120 that you're going to have a lot of recirculation. It's not going to go well. Look at my RTI. It's in the 70s. That's just not going to be good. So I know right away if I look, at my racks, I'm going to have a lot of hot spots. Unacceptable. So here I either need to drop from 40 kW down, or I need to put more air in the room, one or the other. So in all of these cases, all of these N cases, N+1, sometimes customers want N+2. Pick the two. I usually pick the ones that are apart, diagonal from one another, right directly across. Or I pick side by side for N+2 and run a case to see how it performs. And if it doesn't perform well, let them know it. It's not going to be a good day at the office if these things are running too hot. So I wanted to show you a few others as well. It's 9:55. I'm trying to be sensitive to time. I do see some single-sided systems. In particular, I see them from kind of older supercomputer sites. I was working on one at Sandia National Labs, and they're set up a little bit differently. They're set up like this. So they have, and let me just again clean that up a bit so you can see it. So you have air coming out of one side and blowing through a diffuser wall down the line. This is asymmetrical from an air delivery point of view. You can tell by looking at it. Generally, what you run into here is high velocity along these edges. So right here, you'll have high velocity coming out across, causing leakage to occur on this end. And the problem, therefore, is by the time you get down here, you don't have any air left because it went in here and up into the ceiling, and there's nothing left. So you're leaking up front and you're starving further down the line. Very classical kind of problem. This is how they did them a lot before they went to dual fan walls. And you'll see in this design, of course, we're going to have that same problem with the temperature leaking. So let's take a slice at 6 feet. We'll go up high on the rack and take a look. And let me, again, hit the Y key and normalize it with N. Take perspective off. I can, again, share this with you if you want. So let me copy this and put it in the Control V. So it's in the chat if you want to see it. And you see it's leaking, you know, and again, high velocity on this end. Look at the leakage right there. It's coming right out into the cold aisle because the pressure differential here is not in the right direction. It's actually inverted. And I think maybe in this one, the pressure is a little scaled a little bit better, so you're able to see it. Let me see. I was reviewing these last night. No, not really. I'd have to set the pressure scale on that because we've got the way they built these is there's quite a bit of resistance in these diffusers because if they lose a cooling unit, they want this flow to be uniform. So that's why the pressure is higher over there, and that tends to skew the color band. So I would have to adjust the range. But I don't think there's necessarily anything here else. The path lines from the yeah, that's a pretty good shot right there of the same problem. This is a common problem you have. So there you go. It's a pretty picture, but high velocity, right? High velocity coming out of them, they bang into each other. It causes high pressure because again, we're training on velocity pressure and it starts to leak. It starts to leak through the rails. So that was one I wanted to show you. What else do we have? Effective narrow aisles. I wanted to yeah, and I did this on purpose just to show you again what happens. Here, let me first show you the model itself. So these are just outputs. Again, I can share this entire report with you if you would like. So this is Control V. So in your chat box, there's the link to this one. And here we've got the similar problem. Let's first take a look at our inlet temps. They're okay. I mean, it's conforming. This is what you want. You want everything to be green. That's a good sign. So my recommended temperature inlets are fine. What's my supplier temp look like in this case? So we're supplying at 70. You can use low temperature as a way to get away from compliance problems if you drive temperature low enough, but it's going to be expensive to do that. And you may want to do that in a case where you're in N+1 state because something has failed, or N+2, get the temperatures down a little bit. And it's 9:59, but I wanted to show you leakage on this one. So let's take a look at y = 9, and you see here some problems in that narrow aisle. So I made this one narrow on purpose. You see it's leaking pretty badly. It's coming out between those rails because of no other reason. These are all set at the same load, but the aisle's narrow. So there's pressure being built up in that section, pushing it back through the rack rails. So that's what I wanted to show you today. Take you around CoolSim a little, show you how we do it, show you what we're running into. They are sensitive to leakage. This is also an implementation detail. If any of you are doing design build, you need to remind whoever you're working for that the devil's in the details with respect to performance of these systems. They need to put these racks in correctly. They need to seal the rack around the containment. They need to put blanking panels in place. They need to seal up on top, need to get down on the floor and seal underneath, and then be careful of the rails inside the rack. Lead up the rack, clean up the rack rails and make them tight. Above 40 kilowatts for air, I mean, that's the upper limit. I've done some as high as 44 with air, but the problem we run into, there's just so much volume. You're trying to get so much volume into the room that it becomes problematic. Difficult to get really much above that, in my opinion. And always test N+1 and N+2 in various configurations. So, questions. There's one here from Adam, Kevin. It says, for the models showing detailed path lines, with which granularity did you select for the model output? It's the amount of seed points is correlated to the mesh. So if you're not, the way that we do it automatically, because we automatically set this parameter, is there's these seed points. Path lines are really just seed points. So you generally want your meshes to be at least a million cells. It is listed at the top of the output report. So let me just bring up an output report again and show you that up at the top, I ran this one on fine because I wanted to get the mesh count up high enough to be able to see all the path lines. Path lines are correlated to the mesh. So the denser the mesh, the more you'll have. And if you're not seeing any, turn up your density. By the way, if your density is not in a million cells, you need to get it there because you really want it up in this range, at least for most models. I mean, there's some simple models that don't require that because the rooms are small, etc. But you want your density to be up there, right around. I like to see it near a million. Are there other questions? I don't see any. Okay. Well, listen, I hope you found this useful. We'll continue to do these. These are educational in nature. Not so much of a product pitch, but more of how do you do it? How do you interpret it? We've been doing it a long time here and thought we'd share this with you. If you think it's useful, please let us know and we'll continue to do them. If you have topics you would like us to cover in data center design, let us know and we will review them. Whether it's raised floor, non-raised floor, funky designs, you can give us a crazy design if you want and we'll show you how to model it or how we would model it. We have a lot of experience and are certainly willing to share it with you. So thanks everyone for attending today. I hope you found it useful. Have a good day.